is one of the key optimal control theory and tool for optimization of electric powertrain. Okay. So let's move on. So we're gonna start with for the next couple of weeks, we are going to learn optimal control theories. Okay. By the way, there is a few optimal control theory, courses offered by ME Aerospace and EE department, and I think other department as well. But in this course, we're going to give you quick overview and summary of these optimal control theories, and learn how to apply optimal control theories for electric powertrain optimal control problems. So we will move fast, but we still want to learn how those optimal control theories are derived and how it works, the philosophy and principles behind it, and how we can use it for our needs. Okay, so now it's going to be a little more involved, more theoretical, more mathematical. Okay, so you should ask questions if you have any during the lecture or after, or when you solve problem sets. Okay. All right. Let's start with taxonomy. So this is what it looks like. So there are different optimal control theories. Okay. And I think we can have 3 branches coming out of the optimal control theory. First one is obviously dynamic programming. And then second, there's stochastic dynamic programming for stochastic system. Okay, stochastic problem, optimal control problems. And then there's a variational approach, which is derived from calculus of variations. Okay, and in this course, we're going to learn dynamic programming and variational approach. And I mentioned about ECMS, right? And you will learn how we can derive ECMS from variational approach. Okay. By the way, if you have taken linear systems and trajectory optimization or optimal control coursework, then you're probably familiar with these 2. Okay, linear quadratic regulator, or LQR, or MPC, model predictive control. And these 2 are actually a special case of dynamic programming. We can actually derive these 2 theories from dynamic programming. Dynamic programming is the general form of optimal control. Okay. But in principle, these 3 share very basic principles, but their math branch is different. And one of the different, this stochastic dynamic programming, we're not going to learn in this course, okay? It requires a lot of prerequisite background coursework, okay? So you need to take random process and so forth. You need statistics and probability and random process. And Markov decision process is one of the most popular optimal control theory. Okay, very well formulated. So, quick history of DP. So, optimal control theory was first. It was developed really fast in the early 1960s. So this was right after World War II, and there were Cold War. It was the era of Cold War, where Soviet Union and United States were having this Cold War, and one of their conflicting or competing part was exploring aerospace. So they were shooting rockets for both missile and to explore space. And when they do that, they need to solve this optimal control problem, trajectory optimization problems. And that was one of the motivation the government was supporting and funding these mathematicians. Okay, the mathematicians explored this optimal control, problems. Applied mathematicians, and that's when this optimal control theories blossomed. A lot of both dynamic programming, stochastic DP, variational approach. These were developed very fast. And usually the problem is formulated this manner. Okay. So we have system x dot equals f of x ut, and then we have initial conditions, and we have cost function we want to minimize, right? We might want to minimize or maximize, right? If it's a reward function, then we might want to maximize. And dynamic programming was one branch of that, and so Bellman he's called a father of dynamic programming, and of course he's not the first person, but he derived and then he summarized this field quite well, and then he came up with stochastic dynamic programming, also called multi-stage stochastic decision problems. And then later on, it developed into deterministic problems. So it was first stochastic first. And let's move on to the theory itself. Let's start with principle of optimality. So principle of optimality, if you understand principle of the optimality, it'll be very straightforward you to understand the concept of DP, okay? And the DP itself is actually quite easy to understand. But the challenge is its numerical implementation. Okay, so let's take a look. So if you look at this, let's read out loud. Okay, an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. What does that mean? What that means is, this is an example, okay? We have a, let's say we have a 3-node, and we want to find the optimal path, okay? And what the principle of optimality is stating is that the optimal solution from this initial to final stage must include the optimal solution of the sub-problem. So this example is so simple that it's maybe it's trivial or obvious to see that, but we will see why this is important later on. So what this means, what principle of optimality is saying is that the optimal solution must include optimal solution of the suboptimal control problem. So if, for example, if we solve sub problem going from x2 to x3 is this one, then going from x1 to x3 must include this solution, which means this will be the solution, right? Isn't that obvious? 이게 처음에 들을 때는 좀 obvious하지 않다고 생각을 할 수 있는데요. 조금만 생각을 해보시면 너무 당연한 거 아니야? 하는 생각이 들어요. 근데 대부분의 이론, 공부가 그래요. 이게 조금 특히 더 그렇긴 하지만 대부분의 공부라는 것들이 알고 나면은 당연하게 느껴져요. 모를 때는 어렵게 느껴져요. Anyway, so this is a very powerful principle or finding, okay? If we know this, then we can solve more complex problems more efficiently. Oh, by the way, dynamic programming is a enumeration technique, meaning that DP guarantees a global optimal solution. Do you guys know what enumeration means? Enumeration means for this example, what enumeration means is so evaluating all the combinations and then compare. So what that means is, let's say, this is x1, this is x1, 3, x2, 1, x2, 3, right? Then how many combinations do we have? We have 3 here, we have 3 here. Well, we have 9 combinations, right? So if you want to evaluate all combinations to guarantee finding global optimal solution, then you should enumerate and list all the combinations and find and evaluate their cost. For example, we have this combination, this, and then this, and so total of nine combinations. Right? So you need to add 1 plus 3, 1 plus 2, 1 plus 1, 2 plus 3, 2 plus 2, 3 plus 1, right? But if you use this principle of optimality, you can do this much more efficiently. That's the whole idea, whole point of dynamic programming. So if you go back, the main difference between DP and variational approach is that this one, DP, is enumeration. But variational approach does not guarantee global optimality. This guarantees local optimal solution. But I don't know how many of you have taken optimization theory, but if the problem is convex, or if there is a unique solution, then local optimal is global optimal, okay? But even though variational approach only guarantees local optimal, if your problem is nice, it's not too bad, then it can be a quite efficient method, okay? For example, if you have let me use empty space. Let's say if you have a nice quadratic function, then using optimization techniques can be a very nice approach, because finding local optimal will be global optimal solution. But if your problem turns out to be very noisy surface. Then local optimal can be a huge problem, right? If you start from here, you may end up here. But optimal solutions are these values, right? But these are not very good solutions, right? So in order for you to understand these things, you need to first understand the optimization algorithms, search algorithms. But I will talk more about that next time, okay? Let's come back to dynamic programming. So with principle of optimality in mind, let's take a look at an example. Shortest path problem is one example. Here is advantages and disadvantages of dynamic programming, okay? So it's a model-based approach. It's applicable to nonlinear, non-convex problems. Can handle state control constraints. It's quite flexible, global optimal, and so forth. So, but drawback is it's very computationally heavy, okay? Meaning that, so this example was very simple, right? But when problem gets bigger, DP is still a enumeration technique. So it's a smart, it's a efficient approach, enumeration approach, but it's still enumeration approach. So it's computationally heavy. So it takes long time to find the global optimal solution. So you can think of it as, for large problem, enumeration was unsolvable, right? But if this was taking, I don't know, 1 month, then if you use DP, maybe you can do it in, I don't know, 1 day, right? So it's so much more efficient than simple enumeration. But anyway, let's take a look at this example, okay? So x-axis is stage, y is state, okay? So what this problem is showing is we want to start from C0 and we want to reach stage 3, which means either one of these 3 states, M3, C3, S3. It doesn't matter which state we fall into. We just want to get to stage 3. Okay. And usually stage is sometimes it's time for many optimal control problems, but it doesn't have to be. Some problems, this is not time, okay? Anyway, so if we start from C0 and we want to get to stage 3, how would you solve it? Right? One of the simplest And just dumb approach would be just select best option for the given time, right? Instantaneous optimization, which is also called greedy algorithm. So, for example, starting from C0, you just choose minimum cost, okay, 450, and now you are in C1. And now you have 600, 550, and 600. So you select this one. And now you go to C2. Now you have 600, 550, and 600. So you select again this one, and now you ended up with C3 with total cost of 1,550. Do you think this is the optimal solution? Maybe, but we don't know until we enumerate everything, right? So to find the global optimal solution, we need to enumerate, meaning that we need to look at all combinations, right? And how many combinations do we have here? Here we had 9 combinations, right? How many combinations do we have here?
$27.
27? I think it's more than that.
Mm-hmm.
For example, there's 1, 2, 3, 1, 2, 3, 1, 2, 3.
Wait.
And then we have 1, 2, 3, 1, 2, 3, 1, 2, 3.
Wait. It's not right.
So when I say combinations, it means all path, all trajectory. So it can be this, 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 right? Yeah, all kinds of combinations. So here's 9, right? And then 3. Right.
Oh.
So there's many combinations, and we can do this more efficiently. So based on principle of optimality, we can solve this more efficiently. And let's take a look. So the way we solve this is we solve this backwards in time, from the backwards, okay? The idea of DP is we can solve this. We can solve this subproblem and then solve it backwards in time. And the evaluation, the number of evaluation is much reduced if we do this. So for example, let's start with this example again, okay? Okay. So let's start with this example. For example, principal optimality was stating that from x2 to x3, we know this one is optimal solution, right? And what DP is doing is, once we solve this problem, x2 to x3, we don't have to solve it again. And what that means is, we don't have to care about this. We don't need to think about this. Just evaluate once and that's it. Okay? So this is U star from 2 to 3. Okay? And now we want to solve the entire problem, which is x1 to x3. And now we only have to evaluate 3 evaluations. Okay? So 1 plus 1, 2 plus 1, 3 plus 1. So 3 evaluations. Okay? And now, obviously, this is best path. And now let's look at the number of evaluations. So it was 3 times 3. So enumeration was 9. But here we evaluated 6 times, because initially we were evaluating 1, 2, 3, and then we choose this, and then we delete this. This is no longer candidate, and then now we only have to evaluate this one with this, this, and this. So now we have 6 evaluations. Okay, and when this number of states and number of stage increases, this evaluation number of evaluation reduction, it becomes dramatic. Okay, and this is one example. Okay, so now what's happening here is that we are going to evaluate or evaluate and find optimal solutions from 2 to 3. Okay, 2 to 3. Let's solve all the sub problems. Okay, so for example, starting from N2, 450, 500, 650. So this is optimal. 600, starting from C2, 600, 550, 600, so 550. So this one. Starting from S2, 700, 550, and 400, so 400. And that means you can delete these options. Once you solve it, then you don't have to solve it more any longer for stage 2 to 3 part. You just have to record U star. Memorize what was the optimal solution from 2 to 3. And non-optimal solutions, you can throw it away. Okay. And now let's back up one step. Now let's solve the stage 1, 2, 3 problem. You have 3 states, so you have to solve 3 problems. Okay. So now you have 600, 650, and 750, but the total cost is 600 plus 450 or 450, 650 plus 550, and then 750 plus 400. So which one is the best? It's this option, this control. And this red line indicates your optimal action path. So if you choose that path, then the total cost is going to be this. Starting from N1, C1, S2. And then the red indicates the path. Okay? And now we have to, it's time to solve the entire problem, okay, which is C0 to stage 0 to 3. So now you have 600, 450, 500. So you add this, add these two, then this is the optimal action path, and then this is the total cost. So you can see the entire map of the optimal policy. Which is function of stage and X. What that means is no matter where you start, you know optimal solution. So if you start from C2, this is the optimal solution. If you start from C1, this is the optimal solution. If you start from C0, this is the optimal solution. You can start from at anywhere, right? So that's why it's enumeration. So you know all the solutions. So now let's compare this global optimal solution with the greedy algorithm, instantaneous optimization. The global optimal solution is 1400 with this path, right? The greedy algorithm was this path, right, with 1550. Now you saved 150 cost, right? Okay, so we finished right after DP, how DP is actually computed numerically using an example. And the next part is how DP is applied to solve optimal control problem. And this is actually the tricky part. As you can already feel, DP theory itself is actually quite simple, right? The principle of optimality and backward optimization, it was quite straightforward, right? So we had stage, and then we're solving 2 to 3, and then 1 to 3, and then 0 to 3. The main idea derived from principle of optimality is that once we solve sub-optimal control problem, then we don't have to look at, we don't have to solve it again, meaning that we already know the solution from 2 to 3 then we just need to keep that information and record it, and then use it later when we try to solve bigger problem from 1 to 3 or 0 to 3. So conceptually, theory, very simple. Everybody agrees? But the challenge comes when we start to implement this, meaning that this DP theory is in all discrete space and time, right? So we have X, M, say M number of states, and then N number of states, and then we have given number of control options or path, right? But when it comes to optimal control theory, usually the real world optimal control theory, real world optimal control problem is in continuous time and continuous space, right? There.
교수님 목소리가 안 들립니다.
네. 그래서 so I was saying numerically implementing this to solve real world optimal control problem is the tricky part. That's the challenging part. And I'm going to give you a quick summary overview of that, but it's going to be, if you ever use DP for your research, then you will have to further study this part and spend lots of time. But because it takes a lot of time to learn and experience that that problem, the implementation part. But I will quickly summarize what the problem, what the challenging part is, and what are the approach to resolve that issues. So, for example, in real world optimal control problem, time is continuous, state is continuous. Usually control is also continuous. Sometimes not, then you're lucky. But usually most of the time, control, state, time, all of them are continuous space. But DP is developed for discrete time and space. So to apply and to actually solve it in computer environment, you have to discretize it anyways, right? If you think about it, computer does not have any continuous, it's not analog, it's digital, right? And you need to discretize everything. You are just using, you might be using small grid or fine grid points to make it look like continuous, but no matter what, you have to discretize it anyways. So to solve this problem, usually what you have to do first is define your optimal control problem in discrete manner, meaning that you have to first come up with your system in discrete manner, meaning that xk plus 1 equals to f of x and u, right? And then you need to define what your control inputs are, and you need to define what constraints you have, and then you need to define your cost function, sometimes called value function. And usually, so this cost function can be a tricky part, but sometimes not. But if you can list out all of these, then you're setting up your optimal control problem properly. So once you have all of this information, then you're ready to move on to solving the problem. Okay, but you need to first formulate optimal control problem first using mathematical equations. So for hybrid electric vehicle, control inputs is engine power, usually, and for gear, assuming P2 hybrid or parallel hybrid. And then you have feasible operating region for engine, motor, battery, and so forth. So you have many constraints. And then you have cost function. For HEV problem, cost function is usually the fuel consumption or fuel economy. You want to minimize fuel consumption, and that'll maximize your fuel economy for a given drive cycle. But there are other factors other than fuel consumption, such as NOx, PM, and then sometimes hydrocarbon, CO, and so forth, like emissions. And one thing that you need to also think about, consider, is charge sustenance. So you can put that in here or in here as a constraint. So for example, SOCF must be equal to SOC initial, right? So this is proper way to define charge sustenance, right? But sometimes this is difficult to implement. So sometimes people have been doing this. By putting this in cost function, this will act as a penalty if your SOC deviates a lot from the desired or initial SOC. Okay. At the final at the terminal stage, which is the final stage. Okay. And so that's optimal control problem formulation. So that's defining the problem we are trying to solve mathematically. And then you need to apply DP to solve the problem using the model we have. How do we do it? Right. Well, first we need to let me see. We need to do something like this. So for example, this is the model. This is the initial condition. This is the control input. And then we get next time step state or final state. So if this is initial, then this becomes final. So this is K, and this is k plus 1. And then we get incremental cost, instantaneous cost, meaning that for given states and control, we know the next k plus 1 state, which is state of charge, and then fuel consumption, which is L, right? So that's what we have to do first, so that we can compute these values. So this is sort of like fuel consumption, right? And then this is U1, U2, U3, right? So if you apply U1, then you need to first find out what 700 is, because you don't know before you actually run the simulator. And then you need to find out where this ends, right? So apply U1 and S2. S2 and U1 becomes your input, and then your output should be 700 and N3. And then S2 with U2 now becomes, your output is C3 and 550. And then S2 with U3 will give you output of S3 and 400. So this example was already giving you the entire map of the state transition and incremental cost. But you need to find these first for real world optimal control problem. So you need to do this using your model. That's where model comes in. Okay. And once you have all of this information, then now you can apply DP to do backward optimization and find the path, right? But like I said, the tricky part is the discretization part. For example, this is the problem. So let's say you have a model that takes xk, uk, and then you get xk, xk plus 1, and let's say L k. Okay, so input and output. And looking at these relationships, if you look at it from the DP plane, meaning we have stage and then we have state. This is SOC, and then this is, time. And in this case, let's say we discretized X and U, right? So X was from 0.5 to 0.7. U was from, I don't know, 0 to 100 Newton meter of engine torque. And that'll give you xk plus 1 and lk. But if you draw the DP problem using the model, then what's going to happen is that the k plus 1 will not be right on the states. Do you guys understand what this means? So for example, we discretized X and U. So now this is discretized, right? And then we also discretized U. So we are shooting different options, right? So U1, U2, U3, U4, right? And when you put XK and UK and run the simulation, and you will get XK plus 1, but it's not going to exactly fall on the grid of X. It can fall on anywhere, right? Because it's continuous time and state problem, right? It doesn't necessarily fall on the one of the discretized X. Are you guys following? Any questions? 다 이해하셨나요? 재원 학생 이해하셨나요?
한국어로 한 번만 더 설명해 주실 수 있을까요?
네. 근데 이해를 못 하시면 꼭 그 질문을 해주세요. 네. 지금 다른 사람도 다 비슷할 수 있고요. 그리고 지금 설명을 듣는 게 나중에 독학을 1시간, 2시간, 3시간 하는 것보다 더 낫거든요. 다시 한국어로 설명을 드릴게요. 지금 U하고 X를 그리드로 했단 말이에요. 그러면은 U는 잠시만요. U는 그냥 가상의 넘버를 쓸게요. 10까지 있고, X는 SOC인데 0.5부터 0.01씩 0.6까지 이렇게 있다고 하면, 이게 이제 그러면 Y축이 이제 SOC이고 X고, U는 이제 요 패스가 되겠죠. 여러 가지 선택의 옵션들. 근데 어떤 X와 U의 조합을 인풋으로 넣어주면 그 해당하는 그 컨비네이션에 대해서 각각 XK 플러스 1과 LK가 나오겠죠. 이게 이제 fuel consumption이고, 이게 이제 그 next time step에서의 이제 state SOC겠죠. 근데 요 U도 마찬가지로 그냥 똑같은 evenly spaced 된 어떤 그리드잖아요. 그러면 요 evenly spaced 된 U와 evenly spaced 된 어떤 X 그리드를 입력으로 놓고 쭉 시뮬레이션을 돌리면 그 XK 플러스 1, 이 떨어지는 지점이 여기 있겠죠, 쭉. 근데 떨어지는 지점이 우리 원래 우리가 가지고 있던 요 X 그리드, 요 0.5, 0.51, 0.52, 0.53, 요 그리드에 똑똑똑똑 떨어져야 요 DP 문제가 되거든요. 이해하시겠어요? 요 DP 문제가 되려면 그 다음 스텝에서 떨어지는 스테이트가 요 이니셜 그러니까 요 스테이트와 중에 하나여야 된다는 거죠. 그 그리드에 떨어져야 된다는 거죠. 근데 U와 X의 컨비네이션을 만들어서 그리드를 만들어서 쭉 입력을 넣어주면 그 다음 스텝의 xk 플러스 1 SOC는 여기저기 막 흩어져서 떨어지겠죠. 그러면은 x 그리드에 딱 맞게 떨어지지가 않는다는 얘기예요. 그럼 이 문제를 어떻게 해결할까요? So how do we solve this problem? Any ideas? Anything?
To use interpolation.
Yes. So as stated here, one way to do it is using interpolation, meaning that so this gets tricky. This gets complicated. So when you actually do backward optimization, you must add LK, right? The incremental cost plus the J, K plus 1, meaning that from here to here, J, optimal cost, starting from this node, right? So if you fall in somewhere between, you interpolate the value from this one and then this one, because it's unless it's highly nonlinear, and unless this assuming this grid is fine enough, 촘촘하다면 linear some kind of interpolation should be fine, right? It's a approximation, right? So that's one way to solve. What's the other one? There are two approaches. 자, 또 랜덤하게 돌아갑니다. 이런 문제였거든요. 그러니까 어떤 스테이트가 항상 이렇게 딱 있고, 그죠? 사실 얘네들은 같은 스테이트예요. 다른 스테이지에 있는 같은 스테이트. 그런데 어떤 옵션, 어떤 U 옵션을 선택하면 내가 다른 스테이트로 이동을 하고 있죠, 그죠? 그러니까 이게 X축이 타임이었기 때문에 이제 같은 스테이트고, 그러면은 내가 어떤 시작하는 스테이트에서 어떤 U를 선택을 하면 어떤 다른 스테이트로 이동을 하게 되는 거죠. 제자리에 있을 수도 있고 이동을 할 수도 있는 거죠. 그죠? 근데 이 깔끔한 원래 오리지널 DP는 아주 깔끔하게 스테이트에서 스테이트로 딱딱 떨어졌었죠. 근데 지금 그게 안 되는 거예요. 왜 안 되냐? 아무 생각 없이 U를 이렇게 디스크리타이즈 했잖아요. 그죠? 그래서 one way to solve this problem was to interpolate, meaning that we need some sort of flexibility and we're approximating what the cost should be at these points that are not directly on the grid points. There's another approach. 어떻게 하면 이거를 풀 수 있는 문제로 만들 수 있을까요? 준태? 준태 학생, 뭐 아이디어 떠오르는 게 없나요? 아니면 아직 이쪽 공부 별로 많이 안 했었나요? 그걸 어떻게 할 수 있을까요? 할 수 있을까요? So the second option, second approach is to make our optimal control problem formulated so that it looks just like the original DP, meaning that the initial and final are both on the grid. How do we do that? Well, if we fix state first and then find U that goes from this to this, 이해하셨나요? 그러니까 U하고 X를 쪼개가지고 막 쏘지 말고 이니셜 파이널 X를 정한 다음에 여기에서 일로 가는 베스트 U를 찾으면 되는 거죠. 그리고 여기에서 일로 가는 베스트 U, 여기에서 일로 가는 베스트 U. 그러면 DP 문제가 딱 되죠. 그죠? But then now this becomes we need a different model, and this is called the backward model. Okay, so this is the original model, you know, current state and control action, and then you get fuel consumption and next time step state, forward model. But what we need here is that xk plus 1, and then U and L. Do you guys understand? 왜냐면 이거하고 이거를 픽스를 해놓고 U를 찾고 있잖아요. U하고 이제 요 코스트. 그죠? So now your input is xk and xk plus 1, and then you need to find U and L. So this is called backward model. You're sort of solving it backwards. In many times, this is non-causal. Do you know what causal means? Cause and effect. xk plus 1은 xk에서 u라는 액션을 취했기 때문에 나오는 결과물이죠. 근데 이 모델에서는 시작점과 끝점을 알려주면은 그 시작과 끝을 만들어주는 6을 역으로 찾아내야 된다는 거죠. So you need some sort of inverse model, okay? So just just keep in mind when you try to solve DP, when you try to apply DP in real world optimal control problem, you need to discretize and formulate the optimal control problem so that DP can be applied, but this can be quite tricky. And there are two main approaches. One uses interpolation. Second, you make the optimal control problem into the original discrete DP problem, which requires a backward model. Okay,